So Markov Chain Monte Carlo is kind of produces an output quite similar to bootstrapping in that it produces a list of samples of our posterior distribution through an iterative procedure. But the process by which we produce that list of samples is quite different to the process that we used in bootstrapping. So this is the algorithm on the sort of basic algorithm that I've got on the slide here. Beautifully simple procedure. We'll pick through in a second. Although devil lies in the detail, as we'll also come back to a bit later in actually getting it to work effectively. We've come across this before, of course, so that if you've been through the video on disease progression modeling and how we go about fitting the parameters of the event-based model, specifically the sequence that defines the ordering of events in a long-term chronic disease. So one of the techniques we looked at there for examining the uncertainty on that, on the estimate of that sequence parameter, was the use of MCMC. That was a little bit different because the object there that we were trying to estimate was a kind of a discrete valued thing. It's a sequence of n, a permutation of n integers, whereas more commonly in parameter estimation, we would have continuously valued parameters that we're trying to estimate. And the outline of the algorithm I've got here is a little bit more designed to explain how we sample parameters that have continuous values. Okay, so let's just pick through the algorithm quickly here then. So basic idea is that we start with some starting value, some combination of parameter values as an initial guess. Evaluate the, don't do that quite yet. We start with an initial guess, and then many times we perform the following sequence of events. So we will perturb or draw some new combination of parameter values, X, C, so C here standing for candidate. So we draw a candidate set of parameter values that may or may not depend on a current set of parameter values. So in the first iteration of this loop, xt minus 1 would be x0. So we choose a new candidate position, which may or may not depend on x0, depending on a choice of this proposal distribution Q that we'll come back to. Anyway, given an existing combination of parameters and a new candidate position combination of candidate parameters, we evaluate the likelihood of both of these combinations and compute this value alpha, which is a likelihood ratio, the likelihood of the new candidate position divided by that of the old existing position. Let's ignore these factors of Q here for the moment, and we'll just think of this as a ratio between these two likelihoods. And then we select the new candidate position if that likelihood ratio is greater than some random number between 0 and 1. In other words, we select the new candidate position with probability equal to that likelihood ratio. And otherwise, if we don't select it, then we just stick at the position that we are. And the next sample in our list is just the same as the preceding one. Let's pick through that algorithm in a sort of simple one-dimensional example just to make it concrete. So let me draw an example posterior distribution. Let's suppose it looks something like that. And let's pick some sort of arbitrary starting position, x0. I'm just going to put it here. So just label these axes. So this is x, our unknown parameter, and this is the posterior distribution on x, p of x, given some set of measurements A. Okay, so this is our x0 then down here. Could have chosen that anywhere, happened to choose it there. And so let's evaluate the the likelihood of this, this parameter value. So that's just the value on this axis here. So that's P of x0 given A. Now I'm going to choose some new candidate position according to some proposal distribution, Q of Q that takes as a parameter our current position. Many different ways of choosing this proposal distribution, and we'll come back to thinking about that a bit more later. But one common way of doing it is to make a small perturbation of the current position. So we might, for example, choose the next candidate position from a small Gaussian distribution centered on the current position. So let's suppose for the moment that we're going to do that. There are other choices. It doesn't necessarily have to choose from the current position. So one other reasonably common approach is that you simply define a uniform distribution over a sort of viable range of that parameter, and at each time around that loop you just choose a value from that uniform distribution, so then it doesn't depend on the previous point each time around the loop. But I would say the most common approach is what we're going to demonstrate with here, which is just using a small kind of Gaussian perturbation of our current location. Okay, so let's suppose then that from that perturbation of our current location, we happen to choose a new candidate position. Let's put it over here. So our XC is there. So, okay, that's XC. And then, so let's compute this likelihood ratio. So that gives me something up here. Anyone tell me what what approximately then is the value of this likelihood ratio alpha down here? Anyone make a stab at what the numerical value of that would be in this particular case? Link it in the chat. Let me just talk for a moment while you think about that. Just going back to this factor, these factors of Q. Let's think about what this says here. This is the likelihood of jumping from position X to position, from position Y. So the choice of candidate from current position, whereas on the bottom, we've got the opposite, the likelihood of jumping to position Y from position X. And so if we've got a kind of nice, simple, symmetric distribution like this, then the likelihood of jumping from X0 to XC is the same as the likelihood of jumping from XC back to X0. So as long as, if we choose a sort of simple choice of the proposal distribution like this symmetric Gaussian, then these two factors Q tend to, will cancel each other out. There are situations where that doesn't happen. I'll come back to that in a second. But that's why I'm just going to ignore these factors for the moment. Okay, thank you, Harvey. 1.5-ish sounds about right to me. So that's just the ratio of the likelihood of the candidate position and the original position. Likelihood of the candidate is higher than the original, and I agree. 1.5 is approximately the right value for that. Okay, so what do we do next then? We take that value of 1.5 and we take a random draw from a uniform distribution on the range 0, 1. Well, the maximum value that can take is 1, so we know that our value of 1.5 is going to be bigger. So we pass this test and then set the next element of the next sample in our sequence to be this new candidate position. Okay, so we can then replace XC. Hoping I could, let's see if I can just remove that C without the rest of it. Nope. To write it again. We're going to replace, so we're going to call that XC then X1, which is the first sample in our sequence. Okay, so whenever that likelihood, the likelihood of the candidate position is greater than the current position, this likelihood ratio is greater than 1, and we always accept it. Let's make another little jump here. So now we've moved to position 1, to position x1. Next time round the loop, we generate a new candidate position by now perturbing x1 to get a new candidate. So let's suppose it ends up down here somewhere. So that would be our new XC at this position. Now what's the value of our likelihood ratio? Put it in the chat again, numerical value, approximately. Oops. So certainly going to be, yeah, less than 1, thank you. It's going to be pretty, I mean, the likelihood of our new XC is pretty similar to our original X0, isn't it? So it's going to, I think the new likelihood ratio is going to be about 1 over what we had before, say something like 0.6. So now what happens when we reach our conditional here? So now a likelihood ratio of 0.6. When we take our random draw, there's still a 60% chance that that random number is going to be less than our likelihood ratio. So even though the likelihood of this new candidate position is less than our current position, we're still going to accept it anyway with 60% chance. And so that's the, that's one of the key features of this MCMC algorithm, is that we can still take downhill steps, actually still with quite high probability. And that allows us to make transitions between, for example, different modes of this distribution and explore the distribution as a whole, rather than just finding our way to the maximum. Okay, so with 60% chance, then we will take this new lower likelihood position as our next sample, and with 40% chance, we don't do that and stick with our current position, so that x2 would then be equal to x1. Okay, so that's the algorithm in a nutshell. Beautifully simple. Obviously, sometimes you might leap right out to one of the, to a point that's kind of, on the periphery of the support of this distribution where the likelihood is very low, and that would lead to a likelihood ratio close to 0, making it very unlikely that we'd draw a random number less than that likelihood ratio close to 0, in which case we'd be very likely to stick with the current position. And so, yeah, as I say, beautifully simple algorithm, but also has some amazing properties. So actually you can prove that in the long-term limit, as we continue to execute this loop over and over again, the number of times that the process visits any particular range, let's say x up to x plus delta x here, is proportional to the integral of our distribution over that range. In other words, that set of samples converges to a histogram reflecting this posterior distribution. Okay, makes sense so far? Take that as yes. Okay, so just going back to these proposal distributions a second. So under what situations might we sort of break this symmetry? So there are situations, we'll come back to one in a few slides' time, but just a very simple example of where that gets broken. So let's suppose, I said one alternative way of alternative choice for the proposal distribution might be a uniform distribution over a broad range containing the support of our distribution, and that would be symmetric in exactly the same way. However, what if we chose, rather than a uniform distribution, say a very broad Gaussian distribution, something like that, which is, in some ways a little bit more easy to deal with than a uniform distribution, because we don't have to define the endpoints in quite such a concrete way. But then suppose we, if we look at the difference between the proposal likelihood Q of XC here and Q of X1, those two things are different, aren't they? So the likelihood of us jumping from X1 to XC is QC, but the likelihood of us jumping back again is Q1. And those two things are different. So that's one situation in which we would have to choose the proposal likelihood. We would have to include the proposal likelihoods here in this likelihood ratio. So you have to think, you know, when applying this algorithm, it's one of the things you have to think quite carefully about. Is that proposal distribution symmetric or not? And if it isn't, then you have to be careful to include that factor in here. Okay, let's jump to the next slide. So as I say, beautifully simple algorithm, but devil lies in the detail. And there's quite a lot of things to think about when trying to get this algorithm to work effectively to produce a set of samples of the posterior distribution in a reasonable amount of time. So, you know, wonderful property that the set of samples converges to, you know, to provide a histogram of this distribution. But those proofs of that convergence never really say anything about is how long it takes to produce something that reflects the shape of that distribution, and making sure the algorithm does that via the various choices you can make is more of an art than a science, to be honest. Okay, but here are some various issues and parameters then that crop up in the application of MCMC that we'll have a think about. So first thing is a burn-in. So, you know, I sort of conveniently chose my X0 here to be nicely within the support of this algorithm. So the process starts, you know, sampling sensible regions of the distribution straight away. But in general, of course, we don't know where the support of this distribution is. And so when we make an arbitrary choice of starting point, we might get lucky and land in the middle of the action part of the distribution, but we might not. We might end up, you know, out here somewhere as our X0. And when that is the case, it can actually take quite a number of steps. You know, the process has to sort of wobble around in this tundra of close to zero probability areas. You know, it might go backwards and forwards a few times before eventually it sort of finds its way into the, you know, higher probability area and starts sampling the part of the distribution that they're actually interested in. And the idea of a burn-in is to accommodate that. You know, often we get this kind of set of slightly weird samples at the start of the process while the process finds its way into the action part of the distribution. And so to accommodate that, what's very often done is that we just discard some set of samples at the beginning, and that's called the burn-in. So I'm just going to write a sort of list of samples down here that show that. So the actual set of samples that come out of the algorithm, then I'm going to write as X dashed. So X dashed 1 up to, let's say, X dashed B would be our, I'm going to draw them as vectors actually, because in general, although we're thinking in one dimension in this picture up here, in general, each sample would be multidimensional. So the first XB samples then would be our burn-in, and we simply discard those. So here is my trash bin here. We dump all of those into the trash, never use them. And the first sample that we actually use would be X dash to B plus 1. So I'm going to call that X1. That's our actual first sample that we use as an output of this process. So then moving on to the second bullet point here, another common thing to do is that rather than, even though, so let's assume that we've found the action part of the distribution by the time we get to X1 or X dash B plus 1, very commonly what one might then do is not to just start taking every single sample from there on, but actually to discard the next chunk of them as well, until we get up to some number b plus I being big I being an interval. So we're going to discard the next I samples and then only actually collect the next one after that interval of samples. So we're going to chuck all of those in the trash bin again, and then do the same thing subsequently. So after, we only store every ith sample. So that would be my X3. I'm going to bin this lot. Oops. And then keep going up to the final sample of our list would actually be X-B plus TI. And that would give us our final sample XT. Why would we do this? Seems incredibly wasteful. Why discard these sort of big chunks of samples in between ones that we actually collect? Actually, it's staring us in the face, isn't it? So it says it on the slide, to ensure independence of consecutive samples. What does that mean? Why would consecutive samples not be independent of one another? And what does that even mean? Any thoughts? Back to that picture here. Just give you a moment in case someone's got an answer to this. No. Well, let's think about our, perturbations that we've been making from this small perturbation, small Gaussian distribution. Okay, Sam's given me an answer here. Sample I plus 1 is likely to be close to sample I. So knowing sample I informs us about I plus 1. Exactly right. So the problem is that if we're only making small steps between consecutive samples, each consecutive one is is likely to be very much in the vicinity of the previous sample, rather than being drawn from the distribution as a whole. If we just take X1, it's much more likely to be, in this range of actually relatively low priority, low probability, than it is at the peak of the distribution. So it's quite unlikely that the next sample would come here. Whereas by discarding this set of intermediate samples, we can have a series of samples which are, independently drawn from the distribution as a whole, and would be more weighted towards big modes like this one here, rather than being influenced by current positions. So it does depend on the proposal distribution a little bit, but actually this can be extremely important in practice. There are some situations it doesn't really matter if you can just keep running the whatever's using that set of samples many times. But for example, going back to one of our examples of tractography, the actual process of doing tractography is quite computationally expensive. You don't want to run it billions and billions of times for every single one of a very large number of MCMC samples. So it's important then in order to discover the full range of possible streamlines that we might make from a single point. If we're using MCMC to resample the fiber directions at each point, it's important that each time we do that, we're getting a fully independent sample of the posterior distribution on the fiber orientation at each point every time. So that's one situation where that kind of sampling interval would be important. Okay, what other issues have we got here? So choice of proposal distribution, again, very much an art, and an important art to get right in order to make the most out of MCMC. So first of all, the shape of the proposal distribution. So I've suggested here, using a kind of simple Gaussian, most of the time that's fine. There are arguments for using other kinds of shape. For example, if you know, we have a sort of, you know, example distribution I showed back there was multimodal, but not very strongly multimodal. Suppose we had a much more brutally multimodal posterior distribution that looks like that. Very difficult using Gaussian perturbations to traverse this kind of, you know, wilderness of zero probability in between our two modes, because, you know, the likelihood tails off to zero very quickly of the posterior likelihood, but also the likelihood of making jumps that are anything near the length of this gulf between the two modes of this distribution using Gaussian perturbations is very, very low. So for this kind of problem, you know, it can make sense to use some of the distributions that we talked about a few sections ago, you know, things like the Laplace distribution, this sort of double-sided exponential, or the T distribution, for example, which is sort of Gaussian shapes. Both of these things have heavier tails than the Gaussian distribution, so it's more likely that sort of, you know, moves very far from the mean can occur occasionally. And so those kinds of things can help in these sort of situations where there's sort of big areas of zero probability to traverse to get between different modes. So yeah, that's a sort of, you know, relatively minor thing, I guess. The biggest challenge really in choosing the proposal distribution comes in the size of the, you know, how do we choose the standard deviation of a Gaussian distribution on the perturbations, for example. And that's often a big challenge. So let me try and illustrate that with a particular example. So suppose I'm try and reconstruct my posterior distribution again. Something like this, wasn't it? Two-mode thing. So what's the problem? If we choose Gaussian perturbations that are very, very tiny, what's the problem? I mean, so we, you know, wobble around sort of slowly from this starting point. We get a very high likelihood ratio every time, wouldn't we? Every time we make a perturbation, we don't move very far, so the likelihood doesn't change very much. So we get a likelihood ratio close to 1. So we have very high likelihood of accepting the new candidate position. But the problem, of course, is that if those moves are very small every time, it takes forever to get from one side of the distribution over to the other. So if, you know, for example, if we wanted independent samples, we'd have to make that sampling interval extremely large in order to make sure that we're getting independent samples. And even if we don't, in order to sample this distribution completely, we need a very large number of iterations in order to converge towards that, towards the full distribution. So that's the problem about choosing it too low. So why don't we just set it as very high then? What's the sort of, there's a reciprocal problem if we set the proposal distribution very large. Anyone know what, anyone articulate that for me? I'll draw a picture while you're thinking about it. Let's draw it on a very different scale this time. There's our proposal. No, there's our posterior distribution. Let's suppose we now use a very broad proposal distribution, something like that. Now what happens? Let's suppose we start here, x0. Are we likely to land in the proposal, in the action part of the posterior distribution with our first perturbation? Probably not. We're likely to be anywhere somewhere under this big proposal distribution, more likely to land out here somewhere in the wilderness than we are in the action part of the distribution. So, the vast majority of the candidate positions we get have give us a zero likelihood ratio, so they're not accepted. And so almost every time around that loop, we end up just sticking in the same place over and over again. And so once again, it takes, it's because we only land in the action part of the distribution a very small proportion of the times, it still takes us ages to traverse from one side to the other and to sample the full range of that distribution. So yeah, there's a sort of general rule of thumb that I've written down here, which is to aim for an acceptance rate of something between 20 and 50%. So if that's the case, if you think about it, the acceptance rate up here when we had very small perturbations is close to 100%, whereas down here when we've got very large perturbations, it might be something like 1%. And there tends to be a sort of happy medium size perturbation when we are getting something like 20 to 50% acceptance rate, and that sort of optimizes the speed with which we can sample that whole distribution. One other thing to bear in mind about that, though, is of course, we're only thinking in one dimension here, and that gets, we have to think even more carefully about that when we move into the much more common situation where our vector of unknown parameters has more than one number in it. We've got, a multi-dimensional set of parameters. So even just going up to 2 dimensions, for example, let me recall another example from an earlier section. Remember, we were thinking, actually, no, it was this section, wasn't it? It was just at the start of this section. We were thinking about the posterior distribution on our diffusion parameters D and S0. I had a picture, something like this, I think. And so now, if we think about sampling this, so D is, the sort of standard SI units for D are meters squared per second. And in those units, the numerical value of the diffusivity for water wobbling around in, let's say, brain tissue at body temperature would be something like 10 to the minus 9. So let's suppose that we sort of carefully think about the size of perturbations for our parameter D. Probably we're going to end up with a sensible value of standard deviation of perturbations on D, probably also something like 10 to the minus 9. And that would give us, a set of nice sized steps in D that maybe give us this 20 to 50% acceptance rate. But if we just blindly accept that size of perturbation for our other parameter S0, actually the scale of S0, if you remember looking at the values of S0 in the diffusion data set that we've been using, that has a scale, it's arbitrary units actually, but has a scale something like 10 to the 3. So if we make 10 to the minus 9 size steps along the S0 axis, we basically never move. They'd be very, very tiny perturbations, very much like this situation here. And really, we'd be looking for a perturbation size for S0 of probably something like, I don't know, 10 to the 2 or 10 to the 3. So the point is that we need to set that perturbation size separately for every single one of the parameters that we have, because they might all have their own scales. And the kind of standard approach to doing that is that you start by setting the perturbations on all of the parameters very low, and then one by one increase the perturbation size on an individual parameter until you hit that magic 20 to 50% acceptance rate. Then you know the perturbation size for that parameter, set it back to 0 again, or back to low value again, and then do the same thing for the second parameter, increase it until you get the right acceptance rate, put it back to a low value, do the same for the third, fourth, and so on. So you have to optimize them one by one to then come up with a set of perturbation sizes for each individual parameter to make sure that the overall acceptance rate, oh, sorry, I forgot to say, of course, you know, even though we're not moving along S0, we still got, just through the perturbations of D, we'd still have an overall acceptance rate of 20 to 50%. But we need to make sure that when we see that, it's you know, it's taking into account variations in all of the different components of that X vector. Okay, what else should I say on here? Lots of issues, as you can see. I'm not going to pick through them all, actually. The one other one I'll talk about is non-Cartesian surfaces. So this comes back to the point on the previous slide about this, the symmetry of the proposal distribution. So I gave you one simple example where that can arise, and you know, using say a Gaussian distribution on the candidate position that doesn't depend on the previous one. But actually, one of the situations where it possibly more commonly arises is when we're sampling on non-Cartesian surfaces. And this is something actually that crops up in the coursework, where of course we think about one of the parameters that we can estimate from our diffusion MRI data, which is the principal direction, or the estimate of the fiber direction. That estimate of the fiber direction, of course, is a unit vector, or equivalently a position on the unit sphere. So how would we use MCMC to sample positions on a unit sphere? Oops, let's think about that for a minute. So, you know, one way that we might do it is using a standard parameterization of the unit sphere. Let's suppose we think in spherical polar coordinates. So then we'd parameterize our fiber direction by two angles. Let's say we've got the angle of, what is it, co-latitude, isn't it? Theta or latitude, either latitude or co-latitude, can't remember. But theta, the one that the elevation one, and then the other one is the angle of longitude, phi. Okay, so we parameterize our unit vector in the fiber direction by theta and phi. So then let's suppose we, for each iteration of our MCMC procedure, sampling the posterior distribution on the fiber direction, let's perturb these two angles by little Gaussian distributions. Seems sensible enough. But let's think about the effect of that and whether it's genuinely, whether those perturbations are genuinely symmetric. I can tell you that they aren't. And probably the simplest way to see that is if we think about, say, a point up here, quite close to the pole, the north pole of this sphere, and think about a perturbation delta theta that takes us from this value of theta where we are now, the blue dot, to directly to the north pole. So if we make that perturbation delta theta, there's only one point that we can jump to, which is the point directly at the North Pole. However, if you think about making the opposite perturbation, delta theta, minus delta theta from the North Pole, it's not only this single original blue point that we might end up with. In fact, a perturbation of minus delta theta from the North Pole could put us on any position on the horizontal circle sliced through that sphere at the level of our original point here. So there are actually many, many more points that are the inverse perturbation in theta can take us to than the original forward perturbation of theta, showing us that that proposal distribution is not symmetric. I'm not going to say any more about that because, as I say, this crops up in the coursework, so I'll leave you to think a bit about that. But the same is actually true at any level. You know, so suppose we take a different theta down here somewhere. The number of points on the horizontal circle at this value of theta is greater than the number of points on the circle at a slightly higher value of theta, meaning that the chances of moving from one point on this circle to a point on the higher circle are higher than they are the probability of moving back from the higher point to the lower point. Subtle point, but actually, it's important to get that right in order to make sure that the set of samples indeed converges to the right distribution. So yeah, some subtle things to think about. What else have we got on this slide? Yeah, number of samples. Again, it's much the same discussion we had really with about Bootstrap. Really, it just depends on what you're trying to estimate from the set of samples that you get back from MCMC. And the only way to do it really is to monitor the convergence of a particular statistic that you're trying to derive. Yeah, so all sorts of variations of MCMC in practice. There are whole books on it. For example, this Gilk's book is a classic of theory and application of MCMC. Very nice book. It's what, sort of 25 years old. It's still extremely informative.